Hello, everyone. Today I'm going to describe a data warehouse system that was developed at Google. It's been operational for several years now, and many of the critical internal Google clients use our data warehouse for their analytical needs. My name is Jagan Sankaranarayanan, and I'm going to present this work on behalf of my Google co-authors. Now, if you look at data warehouse design, they are typically skewed by the so-called white whales. These white whales require larger performance, larger, faster, better, higher freshness at any cost. On the other hand, many of the newer clients require fairly sophisticated performance characteristics that are quite hard to achieve. This is the reason we went back to the drawing board and then we actually designed this new data warehouse called Napa, which is good for many workload types. At a very high level, Napa consists of three main components, which is the ingest, the storage, and query serving. An ETL pipeline brings in this tremendous volume of data, which ingests trillions and trillions of rows per day. The way to think about it is that at any point in time, tens of gigabytes of data is being ingested in a Napa. Napa is planetary scale, highly available, and all sort of fault tolerance and redundancy is built into this framework. The key thing about Napa, which is very unusual actually, is that we sort of built the back on materialized views. What that basically means is that every table has tens to hundreds of materialized views. These are consistent with respect to each other. They're consistent with respect to the root table, also consistent across data centers. We serve billions of queries a day, with sub-second latency. The user builds their own dashboard analytical tools, widgets, or collabs, and interact with the system using these dashboards. These are fairly interactive workloads, and there is a need for sub-second query latency. Note that even though sub-second latency is quite important, what is more important is robust query performance. This basically means that there should be a low variance in the response time of these queries. That is easily said than done because the workload has high ingest load, and then the workload changes over time. And if you actually go and buy a commercial data warehouse, they typically require you to buy dedicated hardware for it. On the other hand, our data warehouse runs on internal Google Cloud, which are general purpose heterogeneous machines. Now, the second realization here is that not every application requires millisecond latency or minute freshness, or not every client has unlimited data warehouse budget. The client's data business model keeps changing, which basically means that they always come back to the data warehouse and want to renegotiate or rebalance their query performance, cost, and freshness. Imagine for a data warehouse provider like us, that's a big challenge. You want the same infrastructure to handle hundreds of these clients, yet be able to constantly give different performance depending on their needs. Let me give you three examples. An experimental framework comes to us and says that cost is important to control. We want moderate freshness. We want moderate query performance, but I'm willing to take a little bit hit on freshness. Another client comes to us and says that we want exactly the opposite, right? We want high freshness, low cost, but we are willing to give up a little bit on query performance. Can you make that happen for us? Another client comes to us and says that we are super important. We are external facing. We want great performance. We want high freshness, but we are willing to sacrifice on cost. As you can see, clients come from different extremes of this particular space. Yet you need a data warehouse to be able to provide the performance that they actually require. Why is this hard? Let's look at two designs. A design that couples ingest with storage, and another design that couples storage with query serving. In the first case, you can get great performance, but then you have to sacrifice freshness. In the second case, you can get high freshness, but then you have to sacrifice query performance and consistency. As you can see, there's no free lunch. And in these cases, the choice is already made for you. How is Napa different, right? Napa consists of two components. One is the control plane, other is the data plane. The data plane consists of the same three components, except that they're decoupled from each other, which basically means that things can go as fast as they can. The brain of the system is called a controller that basically keeps the databases in the sweet spot of the client's requirement. The controller uses a principled approach called a queryable timestamp, using which it's actually able to keep the performance in the desired state. I'm going to tell you about the queryable timestamp in the next slide. Now, queryable timestamp is a live marker. It keeps changing all the time. That basically tells the client what is the sweet spot, or what is the spot or the timestamp in which they can actually query the database and get a robust query performance. They can get these desirable properties on the database, that the views are consistent, the number of deltas the query needs to open is bounded and small, and the data is actually available in multiple data centers. As you can see, QT is basically the marker of good performance, and it fits into the whole picture by the control. The data warehouse is pushed and pulled in various directions. The ingestion makes the table less fresh, the indexing makes it more fresh, and the client always needs to open a fixed number of deltas in order to get performance. The controller is able to maintain these competing forces and make sure the databases is in the right spot for the client by actually investing resources where it needs to go. As you can see in this particular figure, we have the same old client, and in the right-hand pane, I show you the provisioning that they have made. The left-hand side shows you the span that gives the right query performance, and the controller's job is to make sure that it takes all these particular parameters in mind and keeps the database in the right performance that the client requires. Let me talk briefly about indexing. The infrastructure is completely built using a database, an existing database inside Google called F1 Query. The F1 Query is used in two different ways. One, to process petabytes of data and transforming the ingestion into updates on the table, deltas, and views. And it also is used for client queries. It is very rare for a database to be used in two different ways with completely different looking workloads. Briefly about query serving. The query serving is not done on the raw disk, but rather there's a service that actually performs aggressive caching and other optimization for the query workers. The key idea here is that the parallelism has a way of sort of magnifying tails. For example, when you have 1,000 workers, a 99.99 percentile in network read and disk tail become your 90th percentile in query latency. How do you control these tails? You can touch a view, and in which case you don't need that amount of parallelism. You can get rid of unnecessary parallelism by actually combining work and making them into fewer parallelism. Or you can actually plan for tails by actually detecting slow operation or starting competing ones. The paper gives a lot of experiments, but I'm going to just focus on one of them. What you see here are these clients from before, and these are the production traces of them. The blue one is our experimental framework. The red one is the low freshness one, and the yellow one is our external facing client. Let's look at just the blue curve. They have a heavy ingest load. They still get moderate performance they wanted, and the cost is actually quite low because given the amount of ingestion, the cost is quite extremely low. Now, what they've actually given off is the freshness. They get low freshness, but have actually a bounded freshness at them. So as you can see, this data warehouse is actually able to, you're able to tune this data warehouse for the client's requirement, and which is the main value add of Napa. All right, I'm going to now summarize our contributions here. Napa is comparable to other systems in the sense that we provide high scalability, high reliability, availability. We take in a massive amount of user load. We take a massive amount of data volume. We are unique in the sense that we actually make the ability to tune to client requirements an important component of Napa. The views are consistently maintained even at the face of trillions of row sets coming in. And we provide robust query performance used by use of materialized view and large number of tail reduction techniques. The paper talks about more than a dozen different techniques that we do to mitigate tails. Now, the rich opportunity with Napa, which we are excited, is that it provides ample opportunity for automation, tuning, and query-driven approaches. The paper talks about quite a number of them, but we will discuss them in a future publication.